This is a cube with side length of 1, and then this constraint of x1 plus x2 plus s is equal to 1. This goes through the 3 points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we have somehow the hyperplane that goes through these 3 vertices of the cube. And the constraint x1 minus x2 is equal to 0. This is still the original constraint that we have from before, so this one, but now embedded into 3 dimensions. So this doesn't change in direction s. So we just have this diagonal, but now as a hyperplane that's stretched out into the s direction, and this then goes through those vertices. And this is now a bit difficult to draw in 3 dimensions. This is this hyperplane. And then we get that our new feasible set is just the intersection of those 2 hyperplanes. So somewhere starting here and going into this direction, and then extending obviously outside as long as s is greater or equal to 0. And so this is now our new feasible set that's embedded into 3 dimensions. So in the sample solution that I will upload, you have a nicer picture than I'm able to draw here, but that's how it looks like.
The final set is the blue one, right?
The final set is the blue one, yeah. So maybe I shouldn't underline this in blue, but everything together, this is the blue set, yeah. Okay. And so
does it continue infinitely to this direction?
It continues in. So here, if we are at the back wall of this cube, somehow we are at s equal to 0. So we don't extend into this direction, because then we would have to make s negative. But it extends infinitely far into this direction, because s can become as largely positive as we want. And this cube is just somehow to visualize where these hyperplanes, these 2 lie, and through which points they go. But obviously those are equality constraints. So we have the whole hyperplanes that extend also in all directions here. And the green one also extends there. So this cube is just a help to visualize, but obviously the feasible set then extends to the left infinitely far, yes. Okay. And what we now still need to do is, so if we have a linear optimization problem that has this feasible set, then we have some objective vector C, which has entries C1 and C2, and we want to do like minimize C transpose X such that we have this A as our feasible set. And so obviously, if we rewrite the feasible set into 1 dimension higher, so we introduce this additional slack variable, we also need to think about how we need to modify our objective function to be now also to consider this 1 variable more. But we obviously still want to keep our objective function value the same. So we only want x to enter there. And so if we do this transformation, we need a new objective function. Let's call this C tilde. And there we just write our old entries of the old objective vector into there. And the slack variable just gets an entry 0 in this new objective vector. And then we can rewrite this problem as minimize this new C tilde times x1, x2, and s, which is, if we write it out, nothing else than c1, x1 plus c2, x2. So we keep the objective values the same, but now we have this three-dimensional feasible set of all x1 minus x2 is equal to 0, x1 plus x2 plus s is equal to 1, and s is greater or equal to 0. So here we see how we can rewrite an inequality as a equality by introducing one new variable, and we have a positivity constraint for this variable. And we will see that if we have more inequalities, we can write them all as equalities if we introduce one new slack variable for each inequality constraint. And this then tells us that we can rewrite all of these inequality constraints as equality constraints, where we get some positivity constraints. And our goal in the end is to have positivity constraints for all the variables that occur. Here we see that we don't have positivity constraints for x1 and x2. And in the next exercise, we will see how we can deal with this case. So how we can rewrite one variable that has no sign constraint as two variables that have now sign constraints. And so this is the second feasible set that we want to have a look at. This is B.
So when we introduce new variable, we increase dimension of feasible set by 1, right?
Yes, exactly.
And isn't it, I mean, problem for our optimization algorithms, or is it better that we change inequality constraints with equality constraints, even though dimension of feasible set increases?
That highly depends on which type of optimizer you are using, I'd say. How can I say? So we'll see basically two versions of the simplex algorithm. So the one version works on constraints of the form ax less or equal b, and the other form works on ax equal b and x larger or equal than 0. So there are different algorithms for these different types of problem formulations. In general, I'd say yes, that it's probably beneficial to have more equalities. Because it's easier to deal with, and also if you have a bunch of equalities, you can also have a look at which equalities are, let's say, linear dependent of each other. So if you have more than n equality constraints, you can always reduce them to just the lowest amount of equality constraint that actually carries the same information. So if you have something like x1 plus x2 is equal to 1 and 2x1 plus 2x2 is equal to 2, then obviously you can throw one of these equalities out. And so if you write it all as equality constraints and then see, okay, what of those equality constraints can I eliminate, then you are also able to make the problem much smaller again. So it's always case dependent, I'd say, what you actually want to do.
Thank you.
Good question, though. Yeah, so let's have a look at part B. So there we have x1 minus x2 is greater or equal than -1, and we have x1 is greater or equal than 0. And our goal is now to have also positivity constraints for this variable x2. Now, obviously, we don't have this in this formulation. So if we just introduce it, we make the feasible set smaller, which we don't want. But we can say that we can write this x2 as some x2 plus minus x2 minus, which are basically the positive parts and the negative parts. So there we say that x2 plus and x2 minus, they should be both greater or equal than 0. And obviously, if my x2 is greater or equal than 0, then I can just set this x2 plus to x2 and this x2 minus to 0. And the other way around, if x2 is less than 0, then you can set x2 plus to 0 and this x2 minus to minus x2, which is then again something that's positive. And if we plug this in here, we have minus x2, which is just again x2. So we see that we can always split this variable into a difference of two positive variables. So
Positive
we
or
get
non-negative?
and
Positive or
non-negative,
non-negative?
yeah. So we get this new condition now, which is x1 minus, and then we replace this x2 by this difference of the positive and the negative parts. And now we have that x1, x2 plus, and x2 minus. Those are all greater or equal than 0. So we see that we can also write variables that have no sign constraints into this difference of two variables that have sign constraints. And this obviously also gives us a feasible set that lives in one dimension higher. And this is now a bit more difficult to draw. So we have something like this, where here we have x1, here we have x2 plus, and we have x2 minus. And then all those positivity constraints, they give us that we live in here this positive octant, so to say. And the only thing that's left is then this inequality constraint here, which if we write it as a less or equal constraint by multiplying it with a -1, we get that minus x1 plus x2 plus minus x2 minus is less or equal than 1. So we get again the equality case for x2 being equal to 0 and all the other variables being x2 plus being equal to 1 and the other two variables being equal to 0. And then if we again draw some cube in there to help us draw the feasible, so the hyperplane, then we get that this goes through those vertices. And so we have this hyperplane here as the bounding one that's that comes from this constraint here. And so if we take everything together, we have that our feasible set is in this plane. Where's back? It's bounded by this line, and then here, and extends into these directions, and we extend into this direction here and here. And then we have everything that's in front of this this intersection here and below this hyperplane that's somehow very skewed and comes out of my drawing plane. Okay.
So we are reducing our optimization problems that have constraints, inequality constraints, such inequality constraints on every variable, right?
Yes, our goal is to reduce the problem to variables that are all non-negative. And we still have here this inequality constraint, but we have seen before that this inequality constraint we can also write as equality constraint by introducing one more non-negative variable. So this then tells us that we can reduce all types of inequalities to this combination of equality constraints of the general form and then sign constraints for the individual variables. Okay, so two important things here to mention. This correspondence of points in the old two-dimensional feasible set and the new feasible set is not one-to-one. So no one-to-one correspondence. Why? If we have some x2 that we write as x2 plus minus x2 minus, and we choose a new point in our feasible set that's the three-dimensional, let's call it a tilde point, where we set the old one plus some constant, let's call it d, and we also take the old negative component, also add a constant d, then this x2 plus tilde minus x2 minus tilde, this is, because the d's cancel, is the same as x2 plus minus x2 minus, which is also x2. So we can represent the same point x2 or the same coordinate x2 in our old feasible set by multiple different versions of splitting into positive and negative parts. So we see that in this direction, the set extends infinitely far because we can always add this constant to both the x2 plus and the x2 minus coordinate. This is one.
So
yep.
There is no one-to-one correspondence between what?
Between feasible points in the original set and this reformulation, because if you have one point in this three-dimensional feasible set, then this whole line, these correspond all to the same point in the original two-dimensional feasible set, because
Yes,
to go back, we subtract x2 plus and x2 minus, and then all of those map to the original point in the original feasible set. So let's write between.
But the existence of those whole new set of points doesn't affect the optimization problem, right? I mean, it doesn't change solution. That's what
it doesn't change the solution. It obviously changes uniqueness of solutions. But in general, we are not so much worried about that as long as we find an optimal solution. But yeah, if we have an optimal point in the old one, then we have also an optimal point in the new one. But in the new one, this minimizer is not unique, because we have a whole family of points that are also optimal. But as long as we look at the existence, it doesn't change things.
Okay, thank you.
Okay. So this is one thing, and the other thing is, again, how do we need to modify our objective function? Again, if we first had minimize C transpose X and the feasible set was B, then we now need to minimize over a new C tilde, and we have x1, x2 plus, and x2 minus. And these should represent this connection to the original x2 coordinate in also in the objective function. And so we have that C tilde has the following entries. So the one for x1 is still the same. The one for x2 plus is also the same. And the x2 minus we have to subtract in this representation. So we have a minus C2 in this new objective vector. And then let's move this down and write the constraints again. Then we have x1 minus x2 plus x2 minus is greater or equal than -1. And all of those variables are now non-negative. All right. So we've seen how we can rewrite those constraints for simple problems. And now we want to do this in a more general form. So for this, we say that, okay, if we have some linear program, we can in general we have a very general form. So we have some variables x and y, and we have this the splitting of the objective function, and then we have some inequality constraints that depend linearly on the x and y, and we have some equality constraints that depend linearly on the x and y. And we did the splitting into x and y because the x's might have some sign constraints and the y's might have not have some sign constraints. So this is the most general form of a linear optimization problem that you might encounter. And now we want to apply what we've just seen in order to rewrite this into either the canonical form, which is just inequality constraints depending on some a and b, or into the standard form, which is equality constraints in a general format and then sign constraints on all the variables that we have in our problem. And these are the two one is called canonical form, one is called standard form, and there are different optimization algorithms that either work with an LP in the one form given or in the other form given. So we need to know how we can transform between the two forms, and also how we can get a general linear optimization problem into either of those forms. Okay.
I have one general question. So
yes.
Historically, why was it important to develop so many forms of, not so many, but at least more than one forms of linear optimization problems? Why have not people who worked in the field developed some kind of standard form such that every software accepts this standard form and everyone writes in that standard form? Everyone formulates the problem in that standard form. Why was it necessary to formulate in more than one way?
So I think this will become more obvious when you talk about dual problems in the lecture. So far you've seen yesterday the KKT optimality conditions, and the dual problem of a linear program is somehow related to this these conditions, and you get that the dual problem of a problem in the canonical form is always a problem in standard form, and the dual problem of a problem in standard form is always one that's given in canonical form. So somehow you always have both forms of the same time, one for the one problem and then the other form for the dual problem to this. And
I understand. Thank you.
This is why it's somehow natural to work with both of those. Also, there are just simply people that prefer the one form over the other form. personally, I think that the canonical form is somehow more the intuitive to work with if you want to understand the theory and understand what's happening geometrically. And the standard form might be the one that's more efficiently to actually implement if you want to solve this problem numerically. So there are always advantages and disadvantages to both forms, and that's why we still have both.
Thank you.
Okay. So let's write down the problem that we want to have. So we have minimization over x in Rn1 and y in Rn2. And we have C transpose x plus D transpose y. And we have constraints AX plus BY less or equal than term vector A. We have Cx plus Dy is equal to some vector B. And we have non-negativity constraints for the X. Okay, so let's first write it into the canonical form, which is, I'd say, always the easier one, because we can split this Cx plus dy is equal to b into two inequality constraints. So we have Cx plus dy should be less or equal than b, and Cx plus dy should be greater or equal than b, which we can write if we multiply it by -1 also as a lesser equal constraint. So minus Cx minus dy is lesser or equal than minus b. And we can also write the x greater or equal to 0 as a minus, and now we can introduce the identity matrix times x should be less or equal than 0. And so we immediately get the canonical form. We have minimization over C transpose x plus D transpose y over AX plus BY less or equal than A, CX plus DY less or equal than B, minus CX minus DY less or equal than minus B, and minus the identity times X less or equal than 0. And so we can obviously write all of those constraints into one big matrix, and then we get minimization of C tilde times x tilde, where x tilde is just the vector where we collect x and y together. And we have the constraint such that A tilde is lesser equal than B tilde. And this A tilde matrix we get by the following block matrix. We have A and B, we have C and D, we have minus C and minus D, and we have minus the identity and a 0 block. And the right-hand side of the fused together inequality constraints is then A, we have B, we have minus B, and the 0 vector. Okay. And if we have that in the original A was in our M1 by N1, B was in our M1 by N2, C was in our M2 by N1, and D was in our M2 by N2. This means that this new matrix is now a matrix that lives in, we have our original number of equality constraints. We have doubled our number of the constraints that were equality constraints before. And we have plus the number of variables that had a sign constraint. And we have in total n1 plus n2 variables. And then all the other dimensions of the b and the x tilde, they follow from this. Okay, so we see that if we have a problem that's written in general form, getting the canonical form is pretty straightforward. Let's see how we can get the standard form. So for this, we saw that the original x variables, they already had the sign constraint. For those, we don't have to do anything. All the constraint or all the variables that were in the y part of the variables, there we don't have sign constraints. So all of the y variables we need to split. And this we can do also in a vectorial form. So we say that y is some y plus minus y minus, where y plus and y minus are two variables in Rn2, and both should be non-negative. Then we have split the y variables, and we have now introduced this non-negativity constraint. And in the inequality constraint from before, so there we have M1 inequality constraints. And so for each of the inequality constraints, we have to add a new slack variable. And this we call then Z. And Z is in Rm1 and is greater or equal than 0. And then we have that ax plus by plus z. So we add the corresponding entry of z to the corresponding inequality, and then we get an equality to b, and this set has a sign constraint. And then all in all, the standard form is then minimize C transpose X. We need to split the D transpose Y into D transpose Y plus minus D transpose Y minus. And we have now a bunch of general equality constraints. So we have AX plus BY plus minus BY minus, again, because of the splitting of Y, and the slack variable Z. This is equal to, sorry, this was called A and here also A. And we have the original inequality constraints where we don't have to add the slack variable. There we only have to do the splitting in the y's. B. And we have a bunch of non-negativity constraints for x, for y plus, for y minus, and for the slack variable. Those are all non-negative. And so we can again collect everything into big vectors and big matrices. So we have a minimization of, again, C tilde transpose X tilde, where X tilde is in, now we have in Rn1, plus we have split the y variables into twice the number of variables, and we have new variables for all the inequality constraints. So this is our new dimension that we live in. And then we have such that A tilde X tilde is equal to B tilde, and we have non-negativity constraints for all the variables. And the new variable vector is just x, y plus, y minus, and z. And the new matrix is the matrix, again, blockwise, A, B, minus B, and the identity matrix. And we have C, D, minus D, and a 0 block. And the B tilde is just collected A and B together, and our objective vector is C, D, minus D because of the split in the y's, and 0 because the slack variables don't enter in our objective function. And so this A tilde, this is now a matrix in R. We have kept the number of constraints the same, so this is still M1 plus M2. But now our number of variables has become much larger, so N1 plus 2, N2 plus M1. Okay, so there you also see somehow the differences. Either you make the problem more simple by adding a bunch more constraints. So if you split the equality constraints, you get more constraints than you had before. And in the other case, we keep the number of constraints the same, but we add more variables. And so this is also then somehow telling you there are optimization algorithms that are better suited to deal with more constraints but less variables, and other ones that don't care about the number of variables but want to have as few constraints as possible. And so this also then tells you of which form you should work in. Okay. And so this is the general approach how you would transfer between the two formulations of general minimization problems. Good. Do you have any questions regarding these transformations? I see there was a question in chat. Yeah, I fixed the A. Thanks. Okay, so we are now almost an hour in. Do you want to take a break? Do you want to continue? I'm fine with both options.
I think it's better to continue and finish early.
Okay. Then we'll do this. All right. So in the next exercise, we will want to have a look at a special version of the lemma of Farkas. So let me first copy it over. This is our exercise. So first, let's recap. What is the lemma of Farkas? And I think in the lecture you've seen two different versions. The one that's more common, I'd say, is that if we have some A that's in R M by N, and we have some C that's in Rn, then we have the following equivalence. We have either the one statement that for all directions S in Rn, where A times S is less or equal than 0, it holds that C transpose S is less or equal than 0. And the statement that's equivalent to this is that there exists some lambda in now Rm, which is greater or equal than 0 with C is a transpose lambda. Now this is the let's say algebraic variant of the lemma of Farkas, and in short, we have seen that what it gives us for our optimality is that if we have a look at the set of all S in Rn, where AS is less or equal than 0, and we take the polar cone of this, then this is the cone of all the columns of A, so of A1 through AM, where A is written as A1, A2, sorry, so the rows AM. And so this is the let's say optimization variant of this lemma. And with this, we immediately get the most important tool in characterizing optimality for our linear optimization problems, which are the KKT conditions or Karush-Kuhn-Tucker conditions, which say that some point x bar in Rn is a solution of the following minimization problem. So minimize C transpose X such that, and now we again write general conditions. So AX less or equal B and DX less or equal than E, where we have M and P, sorry, this is equal constraints. Then this this property that X bar solves this minimization problem is equivalent to the fact that we have some Lagrange multipliers, they're called lambda bar that lives in Rm and mu bar that lives in Rp, such that we have the following system of equations. So we have that the objective vector C plus A transpose lambda bar plus D transpose mu bar, this is equal to 0. We have D x bar is also equal to 0. We have A x bar less or equal to 0. The Lagrange multipliers for the inequality constraints, they should be non-negative. And we have that the product of the Lagrange multipliers with the residual of this inequality constraint, this should be equal to 0. These are the
KT.
Let me think. So obviously, if you do some least squares problem, you minimize over some quadratic function. So there you don't have a linear function anymore. And
Yes, yeah.
it's so
but if
in
it's
general,
linear squares, maybe linearly squares, maybe. But yeah, it's still quadratic.
So these are the KKT conditions for linear optimization problems. There are also KKT conditions for general constrained optimization problems. There they look something like if you have minimize f such that g of x less or equal 0 and h of x equal to 0, then they read like gradient f of x bar plus gradient of g of x bar transpose lambda bar plus gradient h of x bar transpose mu bar. This is equal to 0 and so on. So there are generalizations to nonlinear constraint optimization problems. And so obviously the two are related, but if you talk about some quadratic or least
in general,
squares.
constraint problem, gx and hx are not necessarily linear, right?
Yes, so this could be something like x1 square plus x2 square or something.
Okay,
minus
thank
1
you.
or so. And then obviously, so if g and h are linearly are linear, then these gradient matrices are just the matrices that are stated here. But if they are nonlinear, then you really have to work with the gradient matrices.
Okay, thank you.
Okay, so if you again understand this geometrically, you have here again the feasibility conditions. So dx bar is equal 0, ax is less or equal. Oh, obviously, this should be e and b again, because otherwise it makes no sense. This is b and this is e. Probably again, no. So we have the feasibility conditions here. We have the conditions that we can express the C as a linear combination of the row vectors in A and in D. And if you bring C with a minus to the other side, this is geometrically the same condition as saying that minus C should be in the normal cone. And this lemma of Farkas was exactly the way that told us how we can describe any general element in the normal cone by a positive combination of, again, these row vectors. And so this is then this condition. And we have here the compatibility conditions, which tells us that for the inequality constraints, we need here the positive multiplier. So this only works in one direction, because we have the cone here that only contains positive combinations. And we are only allowed to take rows of A where this constraint is actually active, so where it contributes to the description of the normal cone. And this is what this compatibility condition tells us, that if an inequality is inactive, or is well, we don't have the equality case, then the corresponding entry in this ax bar minus b is not equal to 0. And then for this whole scalar product of lambda and this ax minus b to be 0, we need that the corresponding entry of the lambdas is equal to 0. And vice versa, if one of the entries of the lambdas is actually strictly positive, then this means that the corresponding entry in this ax minus b has to be equal to 0. So then the constraint really becomes active and we have the equality case. And so this is what this additional compatibility condition tells us. And so we see that this lemma of Farkas is a very, very important tool that gives us this characterization of the optimality conditions. And to become a little bit more familiar with it, we want to prove as a variant of this, where we have a look at the equality case. So there we have stated some inequality versions, and we can also have a look at lemma of Farkas in this formulation. So we say that a linear equation system AX is equal to B, where A is some rectangular matrix. So we might have one solution or multiple solutions or no solutions at all. And we can characterize the fact that this has a solution by some, again, condition on A transpose. So if and only if for all U in Rm that satisfy that A transpose U is equal to 0, then also B transpose U is equal to 0. And we should show this in two different ways. So first with the lemma of Farkas in the lecture, and then again using some separation theorems that we also used in order to show the original lemma. Okay. So first, let's do this with lemma of Farkas. So let us have first a look at this condition A transpose U is equal to 0, and B transpose U is also equal to 0. So let for all U in Rm with A transpose U equal to 0, the equation B transpose U equals 0 be satisfied. Then, because the set of all U's where A transpose U is equal to 0, because this is a linear subspace of Rm, we can actually rewrite this as a lesser equal constraint. So this is equivalent that for all U in Rm with A transpose U equals 0, it holds B transpose U is lesser equal than 0. So obviously, if you have equal to 0, then this is also covered. So this also satisfies lesser equal than 0. And if you have lesser equal than 0 for all U's in this set, then you can immediately construct a contradiction if there you had actually some strictly less, because then you can just flip and take minus U, which again still satisfies that A transpose minus U is equal to 0, and then you would get here a greater than 0, and this then contradicts the statement. So we can write this as lesser equal than 0. So we are almost in the setting where we have this first statement of Farkas lemma. So we have just we call this here C and S. In this exercise, we call it B and X, but we have now this inequality constraint. We still work with the U that satisfies A transpose U is equal to 0, but this we can again split into two inequality cases. So this is equivalent to A transpose U is lesser or equal than 0, and minus A transpose U is lesser or equal than 0. So for all U in Rn with this property, it holds that B transpose U is lesser or equal than 0. And we can collect this into one big matrix now. So there we have that A tilde transpose U is lesser or equal than 0, where this A tilde matrix is the matrix A and minus A. Transpose. I think I want here no transpose. B transpose U is lesser or equal than 0. And so by lemma of Farkas, as we've seen in the lecture, this is equivalent to that there exists some, and now because this matrix is larger, we have again we have some lambda that is now in R 2m. And we can split this lambda into, again, something that we call plus and something that we call minus. And the statement in the lemma of Farkas tells us that this lambda satisfies that C, which for us below is the B, is A transpose lambda. So we get here that B is A tilde transpose lambda. And this we can write as A times mu plus minus A times mu minus. And this we can write together again as A mu plus minus mu minus. And so if we define this as the point x, we have shown that x solves A times x is equal to B. And we've also seen that we can do this this conclusion here also in the opposite way. So if we have a general solution x of this problem, then we can split x into, again, positive and negative parts. So we have this statement here, and then we get, again, by the lemma of Farkas, that we arrive at our original statement that we've started with. So here this this also works by splitting x into a mu plus, which is always the maximum of the xi and 0, so all the positive entries of the x's, and mu minus the ith component in this. This is the maximum of all the minus the negative entries, and so we have also the opposite direction here. Okay, so this is how we can obtain this version of Farkas lemma by the inequality version of the lemma that we had in the lecture. But we can also get this by just directly proving it using separation theorems, and so we will see how we can do this. And so let's first start again with one of the statements, and so we start with the solvability of the equation. So let x bar solve ax equal to b. Then we have that for all u with A transpose U equals 0, what do we get? We want to show that B transpose U is also 0, but the B transpose we can write as a x bar transpose U. And if we write this out, this is x bar transpose A transpose U. And there we just assume that this is equal to 0. And so this whole B transpose U is also equal to 0. So this direction is pretty straightforward. For the other direction, let's assume that we have this property. So, well, no. For the other direction, let's do a proof by contradiction, so to say. So let's now assume that this AX equal to B has no solution. Okay. And what does this mean, that this equation system has no solution? We know that this equation system has a solution if B, the right-hand side vector, is in the span of all of the column vectors of A. So we denote the column vectors of A by A1 through A n. So we have that A is A1, the column vector, A2, the column vector, and so on to AN. And if this has no solution, we know that B is not an element of the span of the A1 through AN. Because if this were the case, then we would obviously have a solution. So what do we have here? We have here the span of all the column vectors, and this is a linear subspace, and so especially this is closed linear subspace and it's convex. And so since B is not in this closed convex set, we can find a strongly separating hyperplane. So there exists only separating hyperplane. What does this mean? We have a U in Rm without 0, which is the normal vector to this hyperplane, and we have some alpha and beta in R where alpha is less than beta, and we have that A transpose U is less or equal than alpha for all A that are in this span, so in this closed convex set. N. And we have that the B satisfies that B transpose U is greater or equal than this constant beta. So what we've just shown is if we have some linear subspace, which is the span of the A1 through AN, and we have some B that's not in this span, we can find some separating hyperplane that has a normal vector U. And we can actually find two different hyperplanes, one with the beta and one with the alpha, and B is on the one side of the beta one, and our linear subspace is on the other side of the alpha one. Okay. Now, what does this mean? Remember that we are in this proof by contradiction. So we said that this system has no solution, and so we want to derive now that also this other statement is false. So there is a U which satisfies that A transpose U is equal to 0, but where this B transpose U is not equal to 0. So how do we get to A transpose U is equal to 0? And therefore, we again check that we have here this space that we have a look at is a linear subspace. So if A is in the span, then we also have that lambda A is in the span. For all multipliers or scalars for all lambda in R. And so this especially tells us that we have here this less or equal alpha for all A's in this span. This means that we actually have to here an equal to 0 because all other conditions would lead to contradictions by multiplying this with very large constants. So we get here that actually A transpose U is equal to 0 for all A in this span. And what this mean? This means that A transpose U is equal to 0 for all elements in the span, but especially also for all these vectors A1 through AN. And these vectors A1 through AN are exactly the column vectors of A or the row vectors of A transpose. And with this, we get that A transpose U is equal to 0. Moreover, what did we have? We said that we have here A transpose U is less or equal than alpha, which means that alpha is greater or equal than 0. But we had this strong separation, so the beta is actually strictly larger than this, and thus it's also strictly larger than 0. So all in all, we have that B transpose U, which was greater or equal than beta. This is now strictly greater than 0 and thus obviously not equal to 0. And so we are done with also this other direction. If this linear system AX is equal to B has no solution, then we can find a U in Rm where A transpose U is equal to 0, but B transpose U is not equal to 0. So we can also prove the statement just by directly showing it using the separation theorems. Okay. Questions regarding this proof?
So
yes.
So we reformulated Farkas lemma, right?
Yes.
And in one case we used Farkas lemma itself, right? And in the second case we used separation theorem.
Yes.
Yeah. Okay.
So so there are different versions of Farkas lemma, either for just inequality constraints or for just equality constraints or for a mix of both. And we've seen that because we can always formulate versions of the linear programs into one or the other form, we can also work with one form of Farkas lemma or for the other. And we have seen in the lecture the Farkas lemma for inequalities, and here we have it for equalities, basically. And this is just, again, the proof how those results translate to each other. Okay. So there's one exercise left remaining. And there I wanted to talk a bit about polarity. So in the lecture where we talked about the tangential cone and the normal cone, we introduced also the polar cone. So we said that if K is a cone, we said that the polar cone
I have
K. Yes.
One unrelated question a little bit. So if X is in the interior of X, not relative interior, but interior of X, then tangential cone will generate vectors through all directions, right? And we will get as a result R of n.
Yes.
But it is not the case if we have relative interior, it won't produce affine hull of X. Like we won't have similarity, right? We won't exchange Rn with affine hull of X in case of point being in the relative interior.
Yeah, yes, that's exactly what happens. If X is only in the relative interior, then you generate in the tangential cones directions that span the whole affine hull of this, but nothing that's, let's say, perpendicular to this affine hull. You have to be a bit careful about.
If X is in the relative interior, will tangential cone produce affine hull?
So you have to be a little bit careful because the tangential cone is always a cone, so it starts at 0 because it's only the directions going out from X.
The origin, yeah.
Yes, and the affine hull always lives where the set itself lives. So if you shift the affine hull to the origin, then this shifted version of the affine hull and the tangential cone, those are the same. Yeah. Okay. So in the lecture, we saw that we can introduce the polar cone by saying that, well, these are all U in Rn that satisfy U transpose X is less or equal than 0 for all X in our cone K. And in this exercise, we will have a look at more general definition of polarity, because you can do this construction also for general convex sets. And there you do the following construction. If you have some A in Rn, then you can construct the polar set of this by finding all U in Rn where U transpose X is less or equal than 1. So we have a 1 here instead of the 0 from before. And we will see that for cones, this is actually this gives us the same set. So the polar cone is the same with either definition of polarity. But we will also see that for more general sets, this with definition with the 1 on the right hand side is actually the correct definition, because, for example, if we have a convex hull of some points in Rn, then the polar cone of this is exactly the polytope that has these VIs as normal vectors to some constraints where we have 1 as the right-hand side of the constraint, and vice versa. And in the end, we will see that this means that some very important examples are actually polar to each other. So the unit ball in the infinity norm with this somehow the square or the cube in general, this is the polar set to the cross polytope, so this diamond or the octahedron in 3 dimensions. And this set of this notion of polarity allows us to relate those two sets. Okay, so first let's see that for cones we actually don't break anything by doing the 1 here, and it's obvious to see that if we work with this definition as in the lecture, and we have here less or equal than 0, we obviously also have less or equal than 1. So the polar cone in the lecture is a subset of U in Rn such that U transpose X is less or equal 1 for all X in K, which is the definition of the polar set that we did earlier. And to now go in the other direction, we say that okay, if U is not an element of the polar cone, as in the lecture, then we have that there exists some X in the cone, okay, with U transpose X is some small positive epsilon. Yeah, because if it's not in the element, then it doesn't satisfy less or equal 0 for all X in K. So there is some X where we have here something slightly positive. And then we can again use that we are dealing here with a cone. So we know that lambda X is also in K for all lambda greater or equal than 0, since K is a cone. And so if we especially again choose lambda large enough, so for example, if we choose this greater than this 1 over epsilon, what do we get? We get that U transpose lambda X is lambda U transpose X, which is lambda times epsilon. And because lambda is greater than 1 over epsilon, this is greater than 1. And so we have found a point lambda X in the cone where lambda or U times lambda X is greater than 1. So U is not in the polar set of K where we have the definition as above. So for cones, these two definitions are the same. And so let's see now that if we have special sets, we can actually explicitly write down the polar, and this goes vice versa. And for this, we first need to derive a formula. What's the polar of the polar? And we will see that this is the closure of the convex hull of A, including or union with 0. And so especially if A already includes the 0 and is a closed convex set, then taking 2 times the polar, this gives us our original set A again, because all of these operations don't add any new points. And this we will use in the following tasks. So first, let's show that a double polar is the closure of the convex hull of A, including the 0 vector. Okay, so we can easily check that A is a subset of this double polar. Just by the definition of the polar, we immediately get this. We also have that 0 is contained in any polar set, because 0 times any vector is always 0, which is always less or equal than 1. So 0 is in any polar set. And we also know that any polar set is convex because it's defined by a bunch of inequalities. And so if we have a convex combination of points in this polar set, then this also satisfies the inequalities. And we have that this is it's a closed set. So especially we know that a double polar, this also contains 0 and is closed convex. And this immediately gets that the closure of the convex hull of A including 0, which is the smallest closed and convex set that contains A and the 0 vector. This is contained in this A double polar. So we need to now show the other way around. So to show that the double polar is contained in the closure of the convex hull of A including the 0 vector. And we again do this by contradiction. So let V not in this closure of the convex hull of A and 0. And we again do this by separating hyperplanes. So we have here again a closed and convex set. And we have a point that's not in this set. So we get that there is a strongly separating hyperplane. So this is H with normal vector U and right-hand side B. And it holds that the closure of the convex hull of A union with the 0 vector, this is contained in H less or equal. So the 1/2 space that satisfies U transpose X is less or equal than B. And we have that U transpose V, this is greater or equal than B. And we actually can have somewhere here a strict inequality because we have strong separation. And we also know that we have here this smallest closed and convex set that contains A and the 0 vector, and especially we know that A is a subset of this. All right. What we also know is that 0 is contained in this set. So 0 is in closure convex hull A including 0. So we get that U transpose 0, which is 0, is less or equal than B. And because we have here a strict inequality, we can choose without loss of generality B to be greater than 0. And now we want to show that this V is not in this double polar. So we again need to construct here an inequality where we have a 1. And so you can do this by normalizing the U to a U prime, which we get by dividing U by this scalar B. Now, what do we now get is we get that just by a reformulation that A, which is a subset of the closure of the convex hull of A including 0, this is a subset of this hyperplane where we replace U by this U prime, and well, we have a 1 on the right-hand side. And we have that U prime times V is greater than 1. Okay. Now, what does this mean? This means that all points in our set A, if we calculate A transpose U prime, those satisfy that this inner product is less or equal than 1 for all A in A. And from this, we get that U prime is in the polar set of A. But we have here that U prime transpose V is greater than 1. And this especially means that V is not an element of the double polar of A, because we have found an element in A polar such that this inner product is strictly greater than 1. And this is now our converse direction. If V is not in this closure of convex hull of A including 0, then V is also not in this double polar. And this means we are done here. We have now shown that A double polar is exactly this closure of the convex hull of A, including 0. Okay. So maybe let's do the part C and D still, and then the remainders are just consequences of what we've done so far. So part C says that if we have one convex set that's given as a convex combination of some points, then we get the polar as the all points U that satisfy constraints U transpose V less or equal 1 for all the points that we originally had as a description of this convex hull. How can we see this? We immediately have that the polar of P, which are all U in Rn, such that U transpose V is less or equal than 1 for all V in P. All these U's satisfy all of those inequalities constraints. And so this set is contained in the set where we reduce this number of inequalities to just those that are given as the points in this description of the convex hull. So this is contained in the set of all U in Rn, where we only have that U transpose Vi is less or equal to 1 for all I from 1 through M, because we just select a few points from this P. For the converse direction, we need to show that any U that's in this set is also in the polar. So let X equal sum over lambda I Vi, which, because P was this convex combination, we know that all X in this P satisfies such a description with lambda I summing up to 1. Then if U is in the set of all U in Rn such that U transpose V is less or equal 1 for I between 1 and M, we get that U transpose X is equal to the sum over the I's U transpose lambda I vi, which is less or equal, because we know that the inner product of the u's and the y's is less or equal 1, and we have here convex combinations, so all the lambda i's are greater or equal than 0. This inner product is less or equal than 1, so what remains is just the sum over the lambda i's, and we know that this is equal to 1. And so what we have here is that u transpose x is less or equal than 1, and this holds for all x in P, and this means that then u is in this polar cone of P. Okay. And now lastly, so we have that if P is this convex hull of the points, we can write this as a bunch of the polar set of this as a intersection of some half spaces. We can do the opposite if we have some Q which is given as a bunch of points X that satisfy that AI transpose X is less or equal 1 for I from 1 through M. We get again a description of the polar cone as now the convex hull of these AIs. But under one specific constraint, so this holds if and only if we have seen that the 0 has to be in every polar set. So for the polar set to be the same as this convex hull, we need that the 0 is already in this convex hull. So we don't get any additional points because we need the 0 in the polar set. Okay. How can we prove this? Is we want to prove the this direction of the equivalence. We don't have to do anything because we know that 0 is in the polar set of Q because it's in any polar set. And so if we can write this polar set as this convex combination, this means that 0 is in polar set which satisfies this. That we can write this as this convex hull, and so we have nothing to do. For the other direction, we have to work a little bit harder. So we assume that 0 is in this convex hull, and we want to show that the polar set of Q is given by this convex hull of the AIs. And to show that these are the same, let's introduce an abbreviation. Let's call Q prime exactly this convex hull of a run through AM. And our goal is to show that this Q prime is the same as the polar set of Q. Okay. If we have this description as this convex hull, we have seen in part C that the polar set of this Q prime, which is the polar set of this convex combination of the vectors, we can write as the original set Q, because this is exactly the set which has these AIs as the normal vectors of a bunch of linear inequality constraints. So now we want to somehow show that the Q prime is the polar of Q, and to get the polar of Q, we take the polar sets on both sides. So we get that if we take Q prime and the polar end of this, the polar set, this is the same as the polar set of Q. All right. And what do we get from this? From this we get that because we have here the double polar of Q prime, we have seen in part B that this double polar of any set we can write as the closure of the convex hull of Q prime, including 0. So totally we have that this Q, the polar set, is the closure of the convex hull of Q prime, including 0. And we have assumed that 0 is in this convex hull of the AIs. And so because we have abbreviated Q prime to be exactly this set, we have that 0 is an element of the set Q prime. And so we get that here adding the 0 vector, this doesn't introduce any new points. And because the set Q prime is already convex, and because it's a convex hull of finitely many points, it's already closed, we get that this set is exactly the same as Q prime. And so we are also done for the converse direction. We have that if 0 is in this convex hull, then we can write the polar of Q as exactly this convex hull. Okay. And I think with this, I want to conclude for today. Again, as a consequence, we get that, for example, those two sets are exactly polar to each other. So if we can write the unit square as the intersection of those 4 inequality constraints, then those 4 inequality constraints are exactly the corners of this cross polytope, and we take the hull of this convex hull of this, and vice versa. So we have this nice interdependence of the two sets, and so in part G you just have to find proper descriptions of those two sets, one as convex combination of all the corners, and once as an intersection of a bunch of half spaces. Okay. And with this, I think I want to conclude today. For you get the sample solution for all the remaining exercises. But since it's already pretty late, I don't want to continue till the end and also do those again. Do you have any questions regarding the last exercise left? Okay, if there are no questions left, I'd say thanks for attending today. Thanks for staying longer than our usual slot is normally. And I hope to see you in 2 weeks. Bye-bye.